Hello everyone and welcome back to Math Made Easy. In our previous lecture, we completed the topic of numerical interpolation. Now we are moving to the next major topics in numerical analysis. As is numerical integration, you may already know how to evaluate an integral analytically. For example, this integral fx dx from a to b can sometimes be solved easily using the standard integration techniques. But what happens when the function is very complicated? Or what if we don't know the exact function at all? Or instead we are given only a number of only a table of values? In such situations, the numerical integration provides an approximate value of the integral. So, in today's lecture, we will study or understand the basic idea of numerical integration and why we need it and introduce the Newton codes formulas. So, suppose we want to evaluate this I equals to integral a to b fx dx. So, geometrically, we can see this integral represent the signed area under the curve y equals to fx between this x equals to a and x equals to b. So if the function is simple, we can find this area exactly. But if the function is somewhat like complicated, so instead of finding the exact area analytically, we can approximate it using the numerical methods. So the basic idea becomes this: replace the complicated curve by a simple approximation and calculate the area under that approximation. And this is the central idea behind this numerical integration. So the numerical integration is useful in with several situations. Firstly, when the antiderivative of a function is difficult or impossible to express in elementary functions, you can use the numerical integration. Or when the function is available only through the experimental or the tabulated data, or when we need a numerical approximation rather than an exact symbolical answer. So suppose we have this x as 0, 1, 2, and 3 and 4 and corresponding values of fx of 2. And we may still want to estimate this integration 0 to 4 fx dx. So this numerical integration allows us to do this directly from this available data. So let's just visualize the idea. Suppose this is our curve y equals to fx. And instead of calculating the exact area under this curve, we divide the interval as a closed interval a comma b into a smaller intervals. Then we approximate the curve over each subinterval using the similar shapes. For example, we can take the rectangles, we can take trapezoidals, we can take parabolic arcs, or so on. So the total approximate area gives us an approximation to the integral. So conceptually, your integral is approximately the sum of the simpler areas. So the smaller the subintervals, the better the approximation generally becomes. And although this numerical round off and function behavior also matters. Now let's just introduce one of the most important families of numerical integration method, that is this Newton codes formulas. So the basic idea is to approximate this fx by a polynomial passing through selected equally spaced points. So suppose we have equally spaced points as this x0, x1, x2 and up to xn with the spacing h as xi plus 1 minus xi. And we approximate the function by an interpolation polynomial and then integrate that polynomial. So the basic process becomes this function value leads to the interpolation polynomial, and as you need to just integrate the polynomial. And this produces the Newton codes integration formulas. Now this Newton codes formulas are generally divided into two categories. Firstly, the closed Newton codes formulas. Here the endpoints of the interval are all included. For example, you can take the trapezoidal rule or the Simpson's rule. Now comes another type as open Newton codes formulas. Here the endpoints are not included in the interpolation points. For our numerical analysis course, we will mainly focus on the standard closed formulas listed in our roadmap. So let's just start with the simplest Newton codes formula as this trapezoidal rule. So suppose we want to evaluate the value of I as this integral a to b fx dx, and we want to approximate the curve between a and b by a straight line. So the area under that straight line forms a trapezoidal, and this area of a trapezoidal becomes as half of sum of parallel lines multiplied by height. And therefore this I becomes approximately equals to b minus a divided by 2 times f of a plus f of b. And this is a single interval trapezoidal rule. So let's just briefly derive it. The straight line interpolation between a and b can be written as this p1x as f of a plus f of b minus f of a divided by b minus a times x minus a. And since we are approximating fx by p1x, so this integral becomes approximately integral a to b p1x dx. And after integrating and simplifying, we obtain this integral as approximately b minus a by 2 times f of a plus f of b. So the trapezoidal rule is simply the integral of the linear interpolation polynomial. But what if the interval is so large? Now using only one trapezoidal may not provide sufficient accuracy. So we divide the interval into n equal subintervals. Let this be as h equals to b minus a by n. And the points are this x naught equals to a, x1 is a plus h, x2 as a plus 2h, and up to so on and xn equals to b. So we apply the trapezoidal rule to each smaller intervals and add them. So the resulting formula becomes this integral as approximately h by 2 times fx naught plus twice of summation fxi, where I is starting from 1 up to n minus 1 plus fxn. Or equivalently, you can say this approximately to h by 2 times f naught plus twice of f1 plus f2 and up to fn minus 1 plus fn. And this is called the composite trapezoidal rule. Now we have a quick question where we have to approximate this integral 0 to 2 ex e power x dx with n equals to 4. So let's just solve this example. Firstly, we need to approximate this integral using the composite trapezoidal rule with n equals to 4. So just calculating the step size only here. So h becomes this b minus a by n. It becomes this 2 minus 0 as 4 divided by 4 equals to 0.5. So our x values becomes 0, 0.5, 1, 1.5, 2. And fx values as this 1, 1.6487, then 2.7183, then 4.4817, and hence 7.3891. Now just applying this integral is approximately equals to h by 2 times f naught plus twice of f1 plus f2 plus f3 plus f4. Now just substituting the values, we get this to know this becomes 0.5 by 2 times 1 plus twice of 1.6487 plus 2.7183 plus 4.4817 plus 7.3891. So this becomes this 0.25 times of 26.0865 and hence become approximately 6.5216. So our numerical approximation is approximately 6.5216. Now there is an important question you should remember. For the composite trapezoidal rule, the interval is always divided into n equal parts. Therefore, this h becomes this b minus a by n. And the x values must be equally spaced. Now also remember the coefficient patterns as this 1, 2, 2, 2, 2, and up to 2 and 1. So the endpoints having the coefficient as 1, while all the interior points having the coefficient as 2. And this is a very useful exam shortcut. Now comes the error part. The composite trapezoidal rule obviously has a truncation error of order h square. This means that method is second order accurate. So the error decreases as the step size h becomes so smaller, provided the function is sufficiently smooth. Now we'll study error analysis and numerical integration in more detail and when comparing different integration methods. Now the trapezoidal rule approximates the function using the straight lines. But what if we use a higher degree polynomial? Instead of a straight line, we can approximate the curve using the quadratic polynomial as well. And this leads us to the Simpson's 1/3 rule. And if we want a cubic polynomial, we can obtain it by Simpson's 3 by 8 rule. So our progression becomes this trapezoidal, and then comes the Simpsons 1 by third, and then comes Simpsons 3 by 8 rule. So we will study each of these separately. So just quickly summarize the idea. This trapezoidal rule is basically to approximate a function using a linear polynomial, but if we have to approximate a function using the quadratic polynomial, we need to use the Simpson's 1 by third rule. And then comes the Simpson's 3 by 8 rule as this cubic polynomial. And all of these belong to the family of Newton-Cotes formulas. And that's our introduction to numerical integration and Newton-Cotes formulas. So today we studied about why numerical integration is needed actually, and how integration can be viewed as an area approximation, and introduced the Newton-Cotes family, derived and applied the composite trapezoidal rule. In the next lecture, we will study the trapezoidal rule in detail with a more challenging numerical problem. So in the next lecture, we will move forward to the Simpson's 1 by third rule and Simpson's 3 by 8 rule. So if this lecture helpful, please like the video, share it with your classmates, and subscribe to MathMade Easy. And I'll see you in the next lecture.